Hello, everyone. Can you guys hear me? Okay, cool. Okay, we can probably get started. So, yeah. Uh, so basically, we have two sessions, right? So you can free go to any session. And this morning, I think it was 13 or 14 people. So I'm actually wondering whether those people come in afternoon. But okay. So, okay, give me 1 minute. Okay, so a couple of things. Let's do this one. Um, okay, so I will skip some of the content I talk about in the mornings. So what I skipped is this one. So um, I assuming you guys know, you guys already, actually, I don't know. Um, are you guys using Java or C++? Like, so basically is, I assuming you know how to like, install Java SDK and also install IntelliJ IDE. If you are using C++, I assuming you know how to like install the. If you on Windows, right, then you just install this thing called Mingy W64, and also I put I put the link on how to install that one. Basically plus the Visual Studio code, and also there's a video tutorial on here. Same thing in here. You can just so I think one of the video is for Windows, the other one is for Mac. Okay, so and also I also please check out how to using GitHub and the Git. So yeah, so I'm probably gonna skip the demo for this part because then then let's just directly jump into the content we want to talk about. So let's recap. So last week we talked about the flood field. Flood field essentially is, by the way, in the first couple of weeks, we all gonna talking about the graph. Okay, we all gonna talk about the graph. Then in the week one, the flood field essentially is the 2D grid, right? So then you have 2D grid. So then the way how we representing this one is just using two-dimensional array. Right? So suppose you have m, this is a m by n, then you have m row, n column, right? Then I so in basically is then we say on each cell, you basically your four neighbor is either up, down, or either up, down. Well, basically it's going. This is going down. This is going left, going right, right? So that's your up, down, left, and right, right? So I mean, this is like one of the simplest graph and also one of the very special graph, right? So And also far field essentially is a way you can, starting from a given cell, you can systematically traverse the whole graph, right? So basically that's how we basically did it, right? Right. So basically is so that's what we talked about the last week, right? And also I will go over some of the homework later, okay? Then let's first talk about what we want to talk about for today. Then this week and the next week, we're gonna talking about two other type of the graph, and also the two main graph traverse algorithm, which is the BFS and the DFS. And also we will show why the graph is so important and so popular in computer science, because graph is such general like a way you can modeling, the problem. Okay, so let's start with the standard graph. Standard graph. So there's two major components in the graph, right? So the first one is the node, right? So node, or sometimes we call the vertices, right? Or maybe I should use vertices. I think vertices is a more formal way to talk about this one. Vertex, right? And also the other one is edges. So edges essentially is the number of, essentially is a pair of vertex, right? Right. So assuming you have n node, the number of the vertex suppose is like equal to n, then suppose the number of the edges is equal to m, right? Then edges, we said is a pair of the vertex. So then we have one major distinction between two different type of edges. One of them is the directional, the other one is undirectional, right? Okay, so in the directional one, suppose you have two vertex A and B, then this will be, so for example, AB, because it's a pair, right? It's a pair, A, B is different from BA. And then in the directional one, essentially you can think about this is from, this is to. So basically you are saying I have edges from A to B. In this particular case, A can reach B, but the B cannot reach A. Okay, basically is you know think about the one-way entry, right? So you can go from A to B, but not the other way around. In the undirectional one, then you will not have this arrow. In this case, first is AB will equal to BA. Well, in this case, then the direction doesn't really matter, right? So then basically means A can reach B, at the same time B can reach A. Okay, so this is so because depends on the directional or undirectional. We have two different types of the graph, which is a directional graph and undirectional graph. But the way it works is very similar. That's actually the reason I'm not gonna distinguish that one. So that much, right? Okay, this is this is about this part. Then okay, then the next thing we're gonna see is how to representing vertex is easy, right? Vertex is normally how to representing this one. Basically, it's the data structure for graph. Okay, well, sorry. Let me before I talk about. Let me just define one more thing, which is called a simple graph. Simple graph basically satisfies two conditions. One is there was no repeated edges. For example, if you have A to B, for example, no need to have a three in the unidirectional one or direction. So in the unidirectional one, no need to have a duplicate edges. You can just reduce this one to A and A to B. Okay, you can just reduce this one to here because we are like in many problems you can just there's no need to keep like three edges. It's second one is normally there's no self loop. Self loop would be something like this. Self loop, in some problem you can have self loop, but in some problem you don't really want to have self loop. Self loop will cause you some issues. Okay, so yeah, so that's kind of what we call simple graph, right? Then based on that, then we can just think about the data structure to representing the graph. For the vertex, it's easy, right? I mean, the common one is just an array, or you can also using, I think array is probably array or vector is probably the most common way to represent the vertex. Then the edges, there's a three different way you can representing this one. The first one is the adjacency matrix. The second one is the adjacency list. The third one is edge list. So I'm gonna show a demo on this one. So give me 1 minute. Okay, can you guys all see this one? Okay, so here we have an example. This one has 7 vertices, seven vertices, okay? 7 vertices and 8 edges. And this one is an unidirectional graph because you don't see the arrow, right? You don't see the, the arrow. It's like, so then the first way to representing as an adjacency matrix. But the adjacency matrix in here, you will have 7 by 7. Essentially, is the number of the node. You have 7, so 7 by 7 matrix, right? Then on each matrix, the entry is either 0 or 1. So because the matrix, like the entry is like, we're using the 2 indices. One is the number of the row, the number of the column, right? For example, for example, I don't know whether I can, yeah, so this highlighted one is, let me see, I can, oh yeah, okay, I think this is better. So this highlighted one is on the, well, it's actually supposed to be on the third row, but because it's like index start from 0, you can think about this on the, on the corresponding to like, the vertex 2 to vertex 1. So in here, basically, also remember the from 2. So this is basically from vertex 2 to vertex 1, right? From vertex 2 to vertex 1, we do have edges. That's actually the reason this is 1. Okay, this is 1. Same thing apply to the other one. If you don't have edges, it will become 0. So for example, let's looking at all the neighbor of the 2. 2 is connecting with 0, 1, and 4. That's actually reason in this row. In this row, we have 3, 1, right? 3, 1. They are at the 0th column, 1st column, and the 4th column, representing these 3 neighbors. Okay, so yeah, so in the basically this is how you represent this one in the adjacency matrix. Then a couple of more things, because this is an undirected graph. So if 1 is connecting, for example, if 1 connecting with 2, then clearly 2 also connecting with 1. That's actually reason you can think about Aij will equal to Aji. That's actually the reason, this one is symmetric. Okay, this one is symmetric. Essentially is if you, I don't know how much people know a little bit about the matrix, but if you do the transpose, it will give you the same thing. Essentially what I'm saying here is, for example, the second row, the first, for example, this guy should equal to this guy because this is A21. So this one is A21. This one is A12, right? A21, A12, basically that's like from 1 to 2. Okay, this is another thing. Essentially, then one more thing is if you're trying to get for any vertex where the node it can go to, you just take, for example, the if I'm looking, then you look at the ith row. Ith row will give you all the node the ith vertex can go to. Then the ith column will give you basically which node can reach node I. Okay, so this will be useful in the directional graph. Okay, so that's basically in the adjacency matrix. Adjacency list is relatively straightforward. Essentially, is this will, so you have a list. Okay, you have a kind of like array in here. Then each element in the array is a list. Okay, so this array is essentially corresponding to the vertex, right? Then each vertex like corresponding to a list. This list essentially is the neighbor list. Essentially, is a list of all the neighbor or all the neighbor node, right? So if your vertex is like okay, if your vertex is like from like can map to the index from 0 to n, then this is you can use the array to easily to do that. Otherwise, you can using for example a hash map, right? Hash map. The key will be the vertex. The value will be the list. Okay, so that would also work. Okay, the third representation is the edge list. This is easy, essentially just like because each edges is just a pair. Essentially, is store a list of a pair. Okay, so in the I think the first two representations are more common than the third one, because one of the reasons is in many like graph traverse problem, one of the common operation you will need is I'm currently at this node I. I need to get all the neighbor of of this node. Then in both adjacency matrix and adjacency list, it's very easy. In the adjacency matrix, just get the ith row, right? In the adjacency list, just get the the ith element, which is a list of all the neighbor for that particular node. But in the edge list, it's gonna be a little bit difficult to do. Essentially, is you have to unless this one is sorted based on one of them, then you can do some then you can quickly find that. Otherwise, you have to go through the list, find out all the edges contain that vertex, right? Which is gonna be very slow. Okay, so that is for this one. Oh, sorry, what did I do? Oh, I just dropped. Oh no, I don't want to drop this one. Okay, anyway, okay, so that's for this one. Okay, so yeah. Then the next thing we need to think about is, in terms of the algorithm, like when we measuring the algorithm, right? When we're measuring the algorithm, we like the time complexity and the space complexity. So in the graph case, sometimes it will be governing by both, like the number of the node and the number of the edges, right? So, I mean, there's not much we can do with the number of the vertices. Okay, so if the graph is connected, basically means you can, in the undirected graph, essentially means you can go from any node to any other node. This is what exists a path. Then the number of the, then the n must be greater or equal to n minus 1. because just think about, if you connecting all the n node as like a list, it's need at least n minus one edges. If you have less than n minus one edges, then there must be some disconnected node, right? So if the graph is connected, then that's the case. And also, if in the simple graph case, if it's a simple graph case, then the number of edges also going to be less than or equal to n choose 2, right? Because you're looking at well, I guess this is, we'll talk about undirected graph, but either way, this is roughly equal to half n multiplied by n minus 1, right? Essentially, you're taking, this is number of the distinct pair, right? You can get from n node. That's actually the reason you will have n will be kind of like roughly, kind of like, in this between, right? So it's kind of like a between, n to the n squared. Then we say if n is roughly on the n, then we say this is a sparse graph, right? If n is roughly n squared, then this is a dense graph. Okay, so these are just some concepts you need to know right now. It's not, it's not like in the future, there's a certain algorithm, they will have a different variation, depends on the graph is sparse or dense, because in each cases they can optimize towards a different, the different direction. Okay. So then in the graph, one of the common problem we want to do is traverse the whole graph. Traverse the graph, right? Traverse the graph. So this one, then this will give you like two different, this is the thing we're going to talk about today. Essentially, is the BFS and the DFS, right? So BFS is called the breadth first search. DFS is called the depth first search. BFS is related to one of the depends on this data structure, which is called Q. Then DFS depends on the data structure called stack, right? So Q is kind of like has this property, what we call the first in, first out. And the stack will, so this is called the FIFO. This is called the last in, first out. Okay, so that's called the LIFO, right? Then, so essentially is we will show one of the template how the traverse work. Then essentially is we're gonna show the example for BFS, but if you just replacing the Q with stack, it's just gonna become DFS. Okay, it's just gonna become DFS. However, in the actual reality, like many times you will see the DFS was not calling explicitly graph. They can using the call stack. As a such, you're just using recursion. Okay. So we also gonna show that. We're also gonna show how to. We're also gonna show one like a very generic template how to do that. Okay. So let's first do this one. Okay. So the BFS, right? BFS and any like a graph search, you need to start with a certain like node, right? So suppose I'm just gonna say, you have a start node. This is a node start, right? Then you want to initialize your queue. So you have a queue in here. You have a queue. Okay. I'm writing kind of like the pseudocode, not really the exact queue code. Okay. You have these two things, right? First thing what you want to do is you just push the start. You just put the start this node into the queue. So you're basically gonna say, okay, push this one into the queue. Then the whole process will look like this. You're gonna say while the queue is not empty, So you will basically pop. You basically use you're gonna guess. Okay, you're gonna say this is like current node. Okay, this is the current node. Will basically equal to q dot front. Basically getting the very beginning node. Then after you get that one, then you directly pop this one out. Okay. So then, since you are processing this node, one thing very important is you will set this node as visited. Okay. You will set the current as visited. This is kind of like a common thing in the graph traverse, right? Set current as visited, right? Then you're processing current. Okay, you're processing current. This might depend on the problem, right? So then what you do after you process the current, what you do is this: you basically say for each, for every neighbor of current, right? If the neighbor is not visited, then you just push the neighbor into the queue. Okay, so this is roughly like the BFS, right? This is roughly the BFS. Then just keep processing until at the one time the queue is there's no more element in the queue need to be processed, right? So this is basically is kind of like the rough template about how you write the BFS. It's pretty like standard way to do this, right? So and also as I said, if you want to change it to DFS, you just change the queue to be stack, and also change this queue dot front to be like queue dot top, because essentially queue work like this. Right, this is how you push this element, right? So that's basically is the 5.4 idea. So you push this one in here, then you pop this one in here, right? So this is the whole the template, right? Okay, so then, however, as I said, DFS sometimes we don't explicitly using stack, we're using core stack. So I'm also going to show how to do the DFS for the like the with the recursion version. So DFS with the recursion. Okay, so think about it, you have some function DFS called DFS here. Then you will accepting a node, right? You're accepting a node as a current. Okay, so essentially is this one, right? So first is set current as visited, right? Then you processing current, right? Then again, same thing for all neighbor of current. If the neighbor is not visited, just then just call DFS neighbor, right? Then then in your main method, you can just say, in your main method, you can basically say like DFS, you have a node start, then you can basically say like DFS start. So right, basically is you call this one, it seems like you push this one into the stack. Then every time you call the DFS, it seems like you push node into the stack. So that's kind of like the idea. Okay, so that's like this is like a very rough like the template, how you gonna do that. Okay, so I think it's probably good. Let's see one of the example in here. Okay. Okay, give me 1 minute. Let me find out this one. Wait a minute, I don't have this one here. Okay. Okay, sorry, give me 1 minute. Okay, maybe let me talk about the other topic. Then we see this. Okay. So this is on the like the simple graph, right? Then the next thing we want to talk about is the what we call the generic graph. It's so this basically shows you how why the graph is so popular and why the graph is so powerful. Because in many problems, the graph structure doesn't really explicitly exist, but you can model the problem using the graph. So how we're gonna do that essentially is the problem may have a state, okay? State we can using vertex to representing the state. Oh yeah, I guess that's. Then if you then any like a state transited to a state change, which is the state transition, you can using edges to modeling that. Okay. So once you have this one, then then this one basically then you can use this then you can use vertex and edges to modeling the state and the state transition. Okay. So this essentially is how you can build a graph out of this problem. You can build the graph out of this problem. Okay. So yeah, we're gonna see one of the example, just like using this idea. Then you can see why how powerful this idea really is. Okay. So I mean, right now you probably don't really understand what do I mean by state and the state transition. Okay. Let's see one of these problems, then you will understand. Okay. So what? Oh, no, sorry. Sorry, 1 more minute. Let's see this particular problem. So this is a UCL civil problem on 2016 called the milk pot. Okay, so basically it's this. Farmer John has received an order. Oh, by the way, let me just make this one larger. Okay, so I think this is Yeah, I got a I got a feedback in the morning. You know, the text is too small. So yeah, yeah. Actually, whenever you guys have any like feedback like that, you don't just you can just shout it out. Just let me know because sometimes. Okay, so Farmer John has an order of exactly n units of milk, right? He need to fill essentially like this n m units of the milk, right? So m is like from 1 to 200. Okay, then he doesn't have the milking machine was broken, so all he has is he has two milk pots of integer size x and y, both x and y are less than 100. So he using this milk pot to basically can measure the milk, right? Then the question is asking say, um, you know, he can perform the following type of the operation. Essentially, three major type. One is he can fill he can fill up one of the pot. He can also empty one of the pot. He can also he can pull from one pot to the other one, right? Or so the question is asking say, okay, uh, you will only allow at the maximum k this kind of this type of operation. Then they ask you about what is the closest you can get. You have a target which is m, right? You have a target which is m. You can only allow this many operation, the k times operation. Okay, so this is a very um, good example about the graph search and also using BFS. We're just gonna explain this one. Okay, so sorry, give me 1 minute. The 2016 February. Okay, let's go back to the whiteboard. Let's just thinking about how to using this idea to representing this problem. Right. First is the state. The state in this case is relatively easy. So this is the milk pound problem. Right. So state essentially is the current volume, well, the current milk in two milk pot, right? So for example, suppose I'm using the one in the example. So so x the capacity is 15, y the capacity is 50. Okay, 14 and 50. Suppose in x you currently have 10, in y you currently have 20, right? So this is like x. Okay, right? Clearly, they cannot larger than that, right? Because otherwise it's gonna be okay. Then let's think about the state transition, right? We have three allowed operations. One is fill, right? Fill. So basically, you can think about you fill x. After you fill x, basically this one will become 14 and 20, right? Right. If you fill y, this one gonna become 10 and 50, right? Or you can just empty x. Empty x, you will become 0 and 20, right? Empty y, it's gonna become 10 and 0. Okay, so I think the first four is relatively straightforward, right? Then the next one is you can pull the water, you can pull the milk from one to the other one. I can pull from x to y because y has 20, x has 10, and y the capacity is 50. So after the pull, so you will get 0 and 30, right? You will get 0 and 30. Then you can also do from y to x. in which case x, the maximum is 14, so you can at the most get a 14. At that time, y gonna left as 16. Okay, so essentially you are saying, if you think about this is a node, there's another 6 node. You will have edges from this one to all these 6, right? So you think about this is right. I'm probably not gonna draw all 6 of them, but you get the idea how the graph can build based on this. So in this case, you don't need to explicitly list out all the nodes. You don't even need to explicitly list out all the edges. Because the edges and the state are, you've kind of like, well, I think that the state probably we need to list it, but the edges you don't need to list, because edges is kind of like implicitly defined by the transition, right? Implicitly defined by the transition. Let's think about the number of the node. So because all this one can only take an integer value, so essentially is x, or the possible value of x is just going to be 0 to 14, right? All the possible value from y is 0 to 50, right? So then we take the combination. So total you will have 15 multiplied by 51, this many different state, right? This is the number of the state, right? However, we do want to point out in this particular problem, these are all the possible states, but not every state you can reach to. Not every state you can reach to. And also, what's the initial state? Initial state, you just have a 2 empty pole. So basically, the starting node would just going to be 0 and 0, right? Starting node is just going to be 0 and 0, okay? Because at the beginning, you have a 2 empty, milk pole, right? So this is kind of like, okay, with this setup, we can write the code. So I'm going to show you how the code can look like. Okay, again, let me make this one larger. Okay, okay. So, yeah, this is just this is just reading the input, right? Remember, x, y are the capacity, y are the capacity of 2 milk pot, right? As we said, the number of the state, we basically define a Boolean variable, essentially say, visited basically means I can reach to this state, okay? I can reach to this state. As I said, because the capacity is x, the possible integer value is from 0 to x. So you will have exactly x plus 1. This meaning, for x, we also have exactly y plus 1. This meaning for y. That's the reason we're using this 2-dimensional array, 2-dimensional Boolean array to indicate whether I can reach to this given state. Okay, so this is number 1. Then I also define some really like a dummy class, which is called a state. State only contains 3 things. One is x, y is easy to understand. X, y essentially is like the current the milk in x and the current milk in y. What does the level mean? Level basically mean, remember in this particular question we say you only allowed to perform up to k this many operations. Essentially is I need to remember how many operations I already performed. How many operations I have already performed. Okay, so I'm using this leveling to remember that. Essentially is how many operations I have already performed so far. Okay, so then again we say we do a BFS. So we define a queue. Each queue is like a state, right? It's just a state. Okay, then initialize is 0, 0, 0 because initially you have a 2 empty pole, and also you haven't done any operation yet, right? You haven't done any operation yet. So I'm just gonna push this starting node into the queue, and because I'm already at 0, 0, so I will mark 0, 0 as visited. Okay, then I have an actual Boolean variable is done. Basically, is can help me to decide whether I can terminate earlier. I will explain that. I will explain that one. Okay, so in here now you see. This is Java, basically the q.pick essentially is the q.front, right? So you get basically this two will get the first element from the queue. Okay, then now I'm trying to process in this one. So I'm gonna increment this level by 1. Okay, so I need to do actual check. I need to do the check what this one is doing. Remember, I have a target I need to hit. The M. M is the target I need to hit. Basically, what this one does is this one basically will just gonna this one will just compute essentially is the difference between the total volume of the milk in 2 pounds versus the target. Essentially, I'm taking the difference, right? I'm taking the difference. Then I'm taking the difference. If this difference is 0, what does it mean? Because I want to performing to reach the target, right? If I already reach the target, I have no need to continue. I have no need to continue. Because this one only say, oh, how close you can get to your target. If you're already at the target, you can there's nothing you need to do. Basically is done. So you have essentially I'm comparing with. So this result essentially is this result store any time your current volume of both milk pound, the difference between the target versus the total volume of both milk pound, right? That's the reason I'm always taking the minimum. I want this diff to be small as I can, right? I want this diff to be as small as I can. So this is this one. Okay. So now after I take the measurement, I need to transit to the next state. Transit to the next state essentially just as the 6th operation was as what I said. I'm filling the X, filling the Y. So basically is filling the X will be full, right? So I will only go there under 2 conditions. If this state has not been visited, this is number 1. Second is I'm still under allowed number of the operation. Okay, if I'm already exist, the number of operation I allowed, then I will not go there. Okay, so that's reason I need to check in there's 2. This is true for all 6 operations. So so I think the first 4 is very relatively straightforward. Essentially is filling the X, so X will be X. Filling the Y, Y will be the full Y, right? Empty X, so X will become 0. Empty Y, Y will become 0, right? Then this is if I go from X to Y. If I putting X to Y, X to Y essentially is I need to figure out which one is smaller. Then I minus this piece from X. Okay, I minus this piece from X. So yeah, similarly Y to X, right? Because you need to consider maybe after pull from X to Y, or maybe there's still some milk left, or maybe the pole X will be empty, right? So this is essentially is right. Then okay, after that I'm getting the result. So it's a pretty relatively straightforward, it's a pretty relatively straightforward BFS problem. Okay. So now the next thing I'm gonna talk about essentially is so we kind of know the BFS, DFS for now. Then the next really important question is when to using what, right? When to using what? So this is a very important, right? So so if okay, so if you traverse the whole. If your goal is to traverse the whole graph, then this two is essentially equivalent. Then the DFS and BFS are equivalent. Okay. So, however, BFS does have this one of the property essentially is what we call the leveling spanning, right? Which we call the level span. This is easy to understand in the tree case. For example, I have a tree. So you can think about, this is a level 1, this is a level 2, this is a level 3, this is level 4. So DFS will have one of these properties essentially is it starts with level 1. It will not expand to next level without exhausting every node in the previous level. Essentially, it first gonna visit, So if I'm writing out the ordering for this one, it might just look like this. So this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9. Sorry, this is too small. 10, 11, 12, 13, 14, 15. That's probably gonna be rough like ordering of how the node gonna be visited. That's the reason you're gonna see it's kind of like level by level by level by level. Okay, so then the advantage for this one is when you reach to this one, you will guarantee whenever you go from start to any node. In the BFS, it will guarantee that will reach there in the smallest number of steps. Okay, it will reach there in the smallest number of steps. That's actually the reason we're using this factor in the previous problem, because the previous problem, it's basically say the number of the operation you can apply is only you can no larger than k. But so BFS will basically say if I'm reaching this state, taking 3 steps, it's just gonna taking 3 steps. But in the DFS case, you cannot guarantee that. You cannot guarantee that. You may reach to that state, but it may take more than 3 steps. Okay, so that's basically the that's actually the reason BFS. In many questions, if you see the word with something like the minimum number of the steps, those kind of things, then it's probably using BFS. That's kind of like, or you say shortest, the one, that's probably the BFS. Okay. Yeah, this is for this one. And DFS, however, on the other hand, has a slightly different property. This is, if you are looking at a solution space, which is a huge graph, suppose you have a huge graph, okay? This one, it's like a huge. So I'm not gonna, yeah. Okay, so you look, but if it contains multiple solutions, for example, this guy may be one of the solution. You have something else. Maybe there's another solution. So then DFS has one advantage essentially is if you have a multiple solution and any solution is all fine, then DFS has the advantage. DFS can find the solution without traverse the whole graph. Thinking about the previously in the BFS, right? This is happening, for example, if the solution is in some very deep layer, for example, solution supposed in the layer K, right? Then if you're using BFS, then essentially you are saying you will not see the solution unless you visit every node from level 1 to level K minus 1. Because you're not going to advance to level K without finish all the node before, right? So, but the DFS doesn't do that. The DFS will go as deep as it can first. That's actually the reason. If you have a huge graph, it's a solution. There's a multiple node is the valid, the solution you're looking for. Using DFS, it can find the solution much faster than BFS. Okay. Yeah, this is, and also DFS also has another thing which is you can kind of see it's using recursion, so it's kind of easy to write. Okay, sometimes, but that's not really a main reason why you should be using that. But okay, so now we're gonna see another relatively difficult problem. This would also illustrate the BFS. This will illustrate one of the problems for the BFS, and also it will show you one of the remedy on how to solving that. So, okay. Okay, so basically this is a lead code problem called word ladder, and this is a very famous one. And you see the difficulty level is hard. I think this is the first hard problem we're gonna actually see. But this is a very classical one, and also it's very good to illustrate this idea. Okay, let's think about this problem. Okay, so you are given three things. One is the begin word, the other one is end word. You also have a word list. Okay, so the begin word, basically the question is asking, say, so okay, every time you can change, the word one position, you can change, the character at one position to any other character. This is what we call, allowed operation. As long as after the change, this the word will still be in the word list. So then, in which case we call this a valid move. Okay. So the question is asking, if I give you a begin word and end word, can you transform the begin word to end word by this valid transformation? Okay. So here's example. Basically say the begin word is hit, right? Hit. The end word is clock, right? This is word list. So one of the way you can do is they also, did they say they want the shortest number of, right? I don't remember. Yeah, shortest transformation, right? Shortest transformation, right? Shortest transformation. So because it's want the shortest transformation, that's actual reason it indicates you want to use BFS. Okay. So let's think about this one. So this gives you the shortest transformation. So for example, hit, you can change the I to O, so become hot. Hot is in the list, right? Then now you can change hot to dot. Just change H to D, right? So the dot. Okay. So dot is also in the list. Then you change dot to dog, right? Change the T to G. Dog is also in here. Finally, change the dog to cock. Just change D to C. Okay. So this will define a valid, this will give you, in this case, it's gonna a 5-word long, right? So that's basically give you this. Okay, let's think about how we can using the BFS to solving this problem. First one is what is the state? State clearly is just a string, right? Just a string. For example, in this particular case, sorry, in 1 minute, let me put this one on. Yeah. So for example, the given example is a hit, right? Right. So that's basically every time the state essentially is the word, right? So the state transition will be interesting. So essentially what you essentially state transition need to satisfy two conditions, right? Number one condition is you change one of the character in the word to be any other character, right? So this is number one. This part is easy. And also the second one is after you do that, you need to make sure this one was still in the dictionary, right? This one's still in the dictionary, because otherwise, if it's not in the dictionary, it's not a valid move. So you have two different ideas to do that. One is, suppose the dictionary is very small, you can build the graph explicitly, essentially say, for every pair of the word, if they are only differ by one character, you can considering they have one. So basically, is method one is like this. Oh. If two words are differ by one character, then there is edges between these two words. Right? However, if the word list is very large, this approach will be very time consuming because you are checking pairwise. So that's kind of like already unsquared because you take a pair of two numbers. If there's a if the number of the word in the word list is n, then this is already unsquared. So you probably don't want to do that. So that's the reason in this case we're using second method. Essentially say we first just do the character replacing, then we just do one more thing to check whether this one is in the dictionary. Okay. So in this particular case, for example, hit. You can think about this one is connecting to essentially is for example, if I replacing A with H with A, right? This one maybe can go to BIT, right? So on and so forth, right? Until the last one probably is I replace the last character in the last position as Z, right? Something like that. So okay, this will exactly essentially is from the neighbor perspective. All of this one are the neighbor of HIT. Then after that one, then I'm checking whether is in the dictionary. Okay. So I mean, because we're gonna check this one very often, So we know one of the data structure we can use is just a hash set, right? Hash set will check this one very fast. Okay. I mean, in theory, it's kind of like constant time, but I mean, yeah, but because this is so, for example, using hash, right? Right. So this is then so okay. So let's think about how many. I mean, just to like, of course, this will basically depend on like how many are actually valid move. But if you think about this one, in the worst case, what would be the number of the possible neighbor, right? Essentially, each character can be replacing by the other 25 different one. So that's like 25 multiplied by the length of the word, right? The length of the word. In this case, it's like 25 multiplied by 3, which is 75. So this one essentially is the number of the possible neighbor for this particular vertex. And in the graph theory, we also call this one called a fan-out. Okay, so suppose this one I call it K. The number of the fan-out is K. This is one of the problems for the BFS. Essentially, is this. Assuming the fan-out is constant, then what's going to happen is you're going to have a huge tree. Essentially, the number of the node in each layer will increasing very fast, right? So for example, DDD, how are we going to do this one? So initially you have 1, then here you have K, now you have K squared. So this is like a level 1, level 2. Then, in the next layer, you're going to have K, right? So you can see this one will immediately become very, very big. Then remember, because the BFS will never go to the next layer without visiting everything in the previous layer, right? So this is a problem, it can, basically is during the processing, at some point, the intermediate node will become a lot. The intermediate node is going to become a lot, right? So how to remedy this problem? One way we can do this is something called a bidirectional BFS. The idea is this, right? Instead of having this huge tree, for example, the height is h. Then in this node, it will have k to the h, right? K to the h. What I'm gonna do is I have a start here, I have an end here. I'm gonna say, okay, I'm gonna do half of this one and half of this. Essentially, is I'm searching from in here. You are searching from top to down, right? You're searching from top to down. Basically, it's always like this. In here, I'm searching bidirectional. Essentially, is then basically what's going to happen is then this height will reduce to half h. This one was also reduced to half h, right? Because the idea is I'm trying to search from start. When this one going too big, I'm searching from end. Then idea is I'm hoping at some point, they will be connected in the at somewhere in here. Then you can see, then in here the number of the middle node will be 2 multiplied by k to the half. So this is kind of like a square root of this so it's gonna be a pretty big save, especially when k is large. Okay, especially when k is large. Now we can see how we implement this one. So this one is actually using what we call the implicitly like the BFS. It doesn't really using the Q. It's using essentially it's because I'm using a set to store all the results are generating from each layer. Okay, so we will see this one here. So let's just see one of these. Okay. So so basically is this. Okay, so I have a start word, begin word, end word. I have a word list. Okay, then I first put all the word list to a hash set. Basically, is hash set is one key thing in here in order for me to speed things up. Okay, then then I have a this is kind of like a beginning set and the end. This is kind of like the beginning word set and end word set. Essentially, you can thinking about this. Beginning set is all the essentially is at in whenever you expand to a next layer, essentially is when you're at layer K, you're gonna generating all the possible state you can generating from layer K to K plus one. Okay, so this is how we kind of do this. So we're gonna see to one ratio. So handling the two base cases very easily. If the dictionary doesn't contain the end word, then because every move has to be in the dictionary. So if end word doesn't contain in the in the dictionary, then there's no way you can there's no way you can do the proper transition to that, right? So this is easy. We just return 0. And the other one is if both are equal, then we can just return immediately. That just one. After that, I put the end word. I put the beginning word to the beginning set, end word to the end set. Then then I will remove the end word from dictionary. The idea for this one is this is kind of like you're marking this one as visited. Okay, this is kind of like you're marking this one as visited. So now I'm just starting with this one. Now start the first one, just layer as one, right? So okay, simple as the case, if the beginning set is already empty, basically means from the previous one you're generating some empty set. Essentially, is there's no valid move you can generate anymore. In which case, basically means the transition is not possible. So you just return 0, right? So this is the key for the bidirectional one. So I'm always generating from the beginning to end. But if the beginning set is larger than the end set, I just do a switch. I'm switching the end set to become the beginning set. Essentially, you can think about for the word transition, it's revertible. It's revertible, right? It's revertible. Just like the example, you can transit from hit to cock. You can also transit back from cock to hit, by reverse the path, right? So this is the idea. This is essentially the trick to do the bidirectional case. Okay, now this M set essentially is the next is the set of the possible word I can generating from the B set. From the B set. Okay, initially this is empty. Now, okay, I'm iterating every string in the beginning set. Then for each string, for the given string, I'm trying all the position for this string, right? Then I'm just replacing the character. So this is a common trick when you do to the character to the index one. So this way you will basically generating all the character from A to Z. Okay, generating all the character from A to Z. Then I'm replacing this character. I'm replacing the character at this position. For basically generating the next possible string. Then I need to check two things. One is if this generating string is already in the end set, which basically means I just have one more step. I can just get my results. In which case I can know my job is done. So this is essentially the successful case. So if the end set contain the generating the one, then okay, then this is good. So just return level plus 1. Then this is basically now I'm checking whether the dictionary contains this word. If dictionary contains this word, that means this is a valid move, right? Because the move has to be in the dictionary. Then I'm adding this one to the next layer of the possible state. I remove this word from this dictionary because this is same as I'm marking this state as visited. Okay, after this one, I will just call the MSET. So essentially, you can think about the MSET is every time you're generating for all the possible word for the next layer, right? So I'm just keeping doing this one until either one of this is would happen, right? So either you have no more valid move you can make, in which case the B set will become empty, or the B set and the N set will have overlap, in which case you will find a valid move. Okay, so this is about this one. Okay, this is a pretty hard problem, but and also this is I think also this is a very classical problem. Very classical problem indicate what the BFS could get into, and also how you can using this thing to counter that, right? So let me also show the C++ version. Come on. Oh, okay. C++ version is in here. C++ version, basically the whole thing is very similar. The only difference is in C++ you're using unordered set, okay, and yeah, and this is how they check whether this one is in the set in the hash in this one or not. Essentially, just call the iterator, find whether it's equal to the end. Okay. Then one other difference is because in Java, string is immutable. That's the reason every time you have to construct a new string copy. In the C++, string is mutable. String is kind of like just a character array. So what you can do, so this will make the code is much simpler, because you remember what is you remember the original character, then you just change the character as along the line. Then after this one you done, just change it back, right? So then the rest is almost identical. Yeah, only one thing I need to mention for the C++ folks is for the large object, remember passing by reference. Okay, remember passing by reference. Just remember this one. Okay, you don't want to passing by copy. That's just not good. Yeah. This is for this one. Okay, I guess I'm gonna talk a little bit about the homework. Sorry, what is going? Oh, it's in here. So, oh, by the way, do you guys have any questions so far? Okay. Yeah. So I will talk a little bit about this three problem, because we talk about ice perimeter switching on the lighter, during the class. So basically, by the way, I already post a solution here, so you can check out, my solution. So I think the most difficult one is this one, Wells Bessie. So let me just talk a little bit about these two. These two are relatively standard from the flat field, just plus some actual twist. Okay. So for this one, if you already did this one, essentially is you have Farmer John has this 2D cell, then this is the position for the cow. They're gonna place in the cow. Then there was two things. One is there is a thing need to measuring whether the cow is comfortable or not. That's basically is if the number of the neighbor is equal to 3, then the cow is comfortable. So first is for this particular cell, for any particular cell, you can only have at the most 4 neighbors, right? I mean, from the problem solving perspective, you need to remember, you need this extra information. Essentially, say for each cell, you probably want to remember how many neighbors you currently have, right? So that's kind of thing you need to remember. So then one of two tricky part. One is if the cow is comfortable, then Farmer John will adding another cow, because it's like comfortable. So basically means this cow has 3 neighbors. So the way you adding the cow, you only have one option to adding the cow, because there's only one spot left for the four neighbor. But the tricky part is the adding process can be cascading. Essentially, you adding the first cow, you may generating more comfortable cow, in which case you have to adding another cow, so on and so forth. So, and also the other thing is the added, initially this one is between 0 and 1,000, right? The position is from 0 to 1,000, see here? But the added cow doesn't have to be in that range. Added cow could out of the range. That's the reason if you try to model in the 2D grid, it's gonna give you some problem, okay? So to remedy that, what I can do is this. Initially, you can think about this is the grid from 0 to 1,000, because you can add things, you know, out of the boundary. So I'm just adding something actual. You know, in this case, I'm just adding exactly the same piece of this one. I'm expanding this one, you know, like this. So, I mean, if you do the calculation, you will actually know you will at the most expand like half of it. But I don't really want to, you know, I just want to make things slightly easier. So I just extend this guy from 0 to 3,000, which means now this one will be from 1,000 to 2,000. Okay, so you need to do some kind of like the shift. Okay, so I think that's the one of the trick, you know, in this particular problem. So quickly show the code. So basically is this, right? So yeah, I'm using this two board to store two information. The Boolean basically shows whether this position contains a cow or not, right? Then this one basically show, okay, at this position, how many neighbors do I have, right? So then again, I'm also having the same like a directional, like you know, the array here. I'm doing the shifting of 1,000. Okay, so I'm reading the position, then I shifting the thing. Then if I have a cow, I need to do a DFS. I need to do a DFS. What the DFS currently does essentially is DFS basically say, okay, I will mark. Basically, this kind of it's a bad naming for the DFS. What this one does is, first is I'm adding the cow here, okay? Because I'm adding the cow, I will need to like mark, you know, because this is indicator to indicate whether this one has a cow or not. This result minus without plus plus, this is just you know, canceling the effect. Then because now I'm checking for the current position to the number of the neighbors. If this one has a 3 neighbor, which means this cow is comfortable. So now I need to add the actual cow. Okay. So then, oh yeah, this is one thing I forgot to mention. So let me just go to here. Right. So suppose you're adding a new cow here. So you will change the number of the neighbor for this 4 neighbor cell, right? Because essentially each cell recorded the number of neighbor for all these 4 cells. You need to increment by 1, right? You could increment by 1. That's what I'm doing. Right. So this is what I'm doing here. Essentially, is I'm go to all the 4 neighbor. I'm increasing the neighbor count by 1. Then if the neighbor contain a cow and the neighbor is comfortable, then this will triggering the adding cow process. Adding cow process essentially is just finding the correct position, because in 4 neighbor you can only add the cow at the 1 position. You don't know which one it is. So I'm just looping all the all the 4 neighbors. If they don't have a cow, that's the only position you can add the cow. So okay, so basically is yeah. So that's pretty much for this one. So this is the the only trick I think is just you need to do the shifting, and also with this extra information to help you to determine how many neighbor for each position, right? Otherwise, it's a pretty standard flood field problem. Oh, sorry, what am I doing? Then the next question is this guy, right? Why did the cow cross road? So this one is also relatively straightforward, because this one, okay, this one is only basically say I'm adding a road between 2 consecutive cells, and I do not want the cow to go to that road. Essentially, kind of like think about is the road is rather like a block. The road is rather like a block. Okay, so back to the whiteboard. Okay, so think about this one. So this is I, this is J plus 1, right? So you are, if there is a road from Ij to Ij plus 1, oh, by the way, the road is bidirectional. What you're really saying is, when you're doing the flood field, you kind of like, you do not want this one to go through this. You do not want this one to go through this. In which case, if I flood field this particular row, I would only want this one to go this 3 direction. Similarly, for this guy, if I want to do the flood field, I only want this one to go to this 3 direction. I do not want to go to the other direction. Okay, I do not want to go to the other direction. So okay, so I think this is the main thing for this particular problem. So other than that, it's also pretty relatively straightforward. So let's see the code. So okay, so one thing here is, if you remember the question we did on the switching the light, you also have this problem. Essentially, is on each cell, you need to remember which row, whether there's any road attached on this cell, right? And in the worst case, you can have 4 different rows, because you only have 4 neighbors, right? So, I'm having, so the way how I did it is I have a 2-dimensional array, and each element is a hash set. Well, this hash set is kind of like, just a little bit of trick, but because just remember, because you need to store your neighbor, whether there's a road, right? So in here, because your neighbor essentially is a pair. Your neighbor essentially is a pair. Essentially have a row column and a row number and a column number. I kind of like just converted this one to be a string. Essentially is I bar J, I bar J. Similarly, J bar I. Okay, so that's like, so that's like kind of like, so the reason is in the hashing, the primitive type is easy. Hashing object in the Java will have some extra stuff. So I try to avoid that. Okay, so that's the reason I converted that object to be the to be the string. So, but the key is I want each object, different object should generate the unique string. Okay, that's the reason I put this little bar between this. So then again, for on each cell, I will know the list of the row. Essentially, it's the list of the block, right? Then in terms of the flood field, so see, okay, this piece of the flood field is almost identical. Only thing is here. Only thing is I get to the next position I need to go to. Then I'm generating this hash key. Essentially, is I'm checking. Okay, I'm getting all the block for current cell. I'm getting all the block for current cell. Then I'm checking whether my neighbor was in the block. Essentially, I can only go there if this road is if there's no block, right? So this is exactly what I show in in that in that one, right? So then the other one is I have a K cow. I basically is I will start with I will iterate every cow. I using each cow as a starting position. Then I do the flood field. Then after that, I will generating this visited the map of the visited two-dimensional matrix. Essentially tell me starting from this given cow what kind of position I can go to, right? Then the question you was asking say how many pair essentially is if okay. So I probably draw a graph to explain what I'm talking about. Because the block could potentially block your thing into several different regions. For example, the block can block to this region. So suppose you have a cow here, and you have another. Oh, I'm just say this is A. Then this is B. Because the block, then A cannot go to B, right? A cannot go to B, but A may be able to visit the C. Okay, A may be visit to C. Then what's going to happen is, if I start with A, I do a flood field, then essentially after the visit, everything here will be visited will be true. Okay, then all the other places visited will be false. Then I can just say, suppose I have another one in here is D, I have another one in here is E. Okay, then I know exactly which cow, the position for each cow. I can just see how many nodes I cannot visit, how many cow I cannot visit to start from A. Okay. Right. So this is to say, after I get this one, I will call this method called get count. What this get count does is, get count basically say looping through the number of the points essentially is the number of all the other cow, right? If this cow is not visited, then I'm incrementing the count. Essentially, that's the kind of the pair I want to do, right? So then I will do this one for all the cow. Eventually, the result will divide it by 2 because that's because if A cannot visit the B, then B cannot visit the A. So I will this pair I will count exactly twice. So that's the reason I'm dividing by 2. Okay. So we are kind of like running out of time. I'm not sure whether you guys can still stay for another maybe 10 minutes. If you can, I'm just gonna describing the last question, which is probably the most difficult one. Again, if you have other things you need to go, just feel free to go. But there is a video, so you can view afterwards. So this is about this problem. Where is Bessie? So this is probably is very considerably to be much more difficult than the previous two. First one is you need to decompose this one into several small problems. Okay, the first one is let me just explain this one. So okay. Number one is this. This is my whole grid. Okay. The first problem essentially is in a sub sub area, I need to determine whether this is a PCL. Okay. I need to do this for all the possible sub areas. That's the reason, the easiest way is you're looking at the top left vertice and the bottom down IJKL, right? So you can just ranging from there, basically is for all the possible this combination, you can just basically different area. So you're using like a flood field as a subroutine to check whether this is a PCL. Okay, so then we need to figure out what is a PCL. So the example was given is like this. For example, if you have something like this, A, B, 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 A, B, A, B. First is by the the number of islands we run last time, we can basically find out how many connected components are there. In this particular case, you have one of the A, you have this two of the A, and you have this B, right? So PCL will satisfy two conditions. Number one is the number of the color. Basically, the color was using as the capitalized letter. The number of the color is equal to 2. Okay. Second one is there is a one color only have one component. In this case, which is B, and the other color, there's another color. You have greater or equal to component. Okay, that's actual reason. You can think about this one. Essentially, is you clearly have something on the color to the number of the component of this color, right? So essentially, is sorry. Oh, this guy is not coming. Sorry, give me one minute. Okay, so basically, the color. Basically, you kind of have a color to the number of the components. So that's kind of like reminds you what we call the frequency table kind of thing, right? So basically, once you run the flood field, you need to generating, kind of like how many color you have, and also for each color, how many different components you will have, right? So then using this information, we can identify for this given region whether it's a PCL, right? So that's also should be relatively, easy. Then the last question is, you want to check whether this is a maximum PCL. What do we mean by maximum PCL? Maximum PCL basically means, for example, if you have one of PCL, the other one basically is this PCL cannot be inside of the other PCL. And also to check this one is also easy because if you have basically do the pairwise suppose you get a list of the PCL, then you can check pairwise whether this one is inside of the other PCL, right? For example, this is IJ, This is maybe, okay. I guess the one I did this one is like, suppose this is well, I mean, yeah, basically it's a PCL in another PCL. Okay, so then you combine everything together, that will give you the answer. Okay, so I'm gonna quickly show the code. So the code is like this. Okay, so yeah, I will. Oh yeah, the bookkeeping thing, right? Because the board is using character, I'm using this one as a visited, right? So visited is always the thing. So directional one and also the PCL. So the PCL essentially is just the I1, I2, J1, J2. I1, I2 thinking about is the left, the top left. J1, J2 is the bottom right. Okay. So then okay. So what I'm going to do is, okay. So this is reading the graph. Then this is say for each. I have a for loop. Essentially, this is basically iterate for all the possible different area, right? Then first I'm checking whether this area is a PCL, right? If it's a PCL, then I'm adding to the PCL list. So how to check a PCL? Check the PCL first. I need to, because I'm reusing the same visited the two-dimensional array. So before I visit, I need to initialize everything to be false, right? They do the initialization. Then these are the two things I'm actually need to calculate from the plot field. Essentially is okay. So number of the color, and also this is kind of like a color frequency table, because in this case each color is mapped to a capitalized letter, so I can just directly map them to an index, right? So this is a standard plot view. This is a standard plot view, right? The only thing is if I reach a new basically this is kind of like the number of island. If I'm reaching the first piece of this island, I find out the color. I find out the color for this area. Then I'm trying to see how many components I already have for this color. If this is 0, then I know that's a new color. So I will incremental the number of the color. Then clearly I'm going to incremental the count for this color as well. So after that, then I will have this, right? So now I'm checking whether this is a PCL. PCL basically have two things. Number of the color has equal to 2. If not equal to 2, it's not a PCL, right? Then I need to find, then after this one, then in this thing, I should only have 2 colors. One of them, the count should equal to 1. The other one, the count should be greater than 1. So if both are satisfied, then it's a valid PCL. Okay. So okay. So I'm adding all the PCL to this PCL list. Then after that, I'm checking, I'm checking whether this is a maximum PCL. Basically, it goes through this list. So this is kind of like, this is actually is a double loop, basically double loop, because inside of this, I'm iterating all the PCL. Then I'm checking. The way to checking essentially is maximum PCL essentially say, I'm comparing the current index with all the other PCL. Basically check whether there's a PCL inside another PCL. How to check that? Essentially is just check the position. Essentially is one of the PCL has to contain the other one. Okay, has to fully contain the other one. This is just with some like simple math, you should be able to figure out. It's not very difficult. Yeah, that's pretty much it. Yeah, so this is this. Okay, so I'm gonna stop at here. So do you guys have any questions so far? Assuming that's no. Again, as always, like if you have any question, you can just if it's a course-related question, for example, regarding the homework, and I actually prefer you can ask, in the channel. Of course, you can also like message me on the Discord, right? You can message me or you can email me. Either way is fine. Okay. I think next week we're gonna see. We're still gonna on this topic. We're gonna see more example about the BFS and the DFS. The reason is this topic is very, very important. So in the UC Civil, 3 major topics. This is one of them. So that's the reason we're gonna stay like we're gonna spend like 2 or 3 lecture on this. I want everybody after this you will feel really comfortable. You can implement the BFS DFS you do the graph traverse. So this is a pretty fundamental, pretty important for the UC Civil. Okay, so okay, I guess homework is already out. I haven't figured out how I can post the lead code solution. Once I figure out that, I will add it to the solution part. Okay. What else? I think that's pretty much it. Okay. I guess I will see you guys next week. Okay. Bye.
Thank you, Bob.